we're going to go over some basics of what's called object-oriented programming. Essentially, this is a way to write software that relates directly to how the real world is organized. And it relates to using what are called objects. What's an object? It's a thing. Well, that's really clear, isn't it? It really is anything. An object could be a car. It could be a user. It could be a client. It could be an email sending module, where a module is one part of the greater overall thing. These are all things. They're all objects. These ones you can kind of relate to the real world. You can walk up and you can look at a car, right? You can see a user of a program. You can, think of a client of a business. This one, maybe I could spell email correctly. Maybe this one, maybe a little more abstract. An email sending module will be that part of a program that's responsible for taking a completed email message and sending it out on a network towards its destination. But they're all things. They're all objects. Okay, good. So, what is object-oriented programming? It's all about code reuse. Your software code needs to be reused. Rather than writing the same thing over and over again whenever you need it, make it so that you actually write it once and can use it in multiple places. That's part of the principle behind object-oriented programming. So, here's how object-oriented programming works. In your code, you're going to define what's called a class. A class is a category of or type of thing. So, where we had our examples before, you could have a car class or a user class, or to drop down to that bottom of the example, an email sender class. Now, here's what a class is. It's a definition of potential property and behavior. Let's make this real world. Let's say we have a car class. What's the potential property characteristics of a car? Well, there would be the color. There would be what body style it is, two-door, four-door, hatchback. There would be what type of engine it has. There would be whether it's a gas or electric car. Those are all properties. And this behavior, a car could accelerate, decelerate, turn right or left, go backwards. These are all property and behaviors of a car. And what a class is describing what it could be if you had one. The class is not something you already have. If you're going to describe the concept of a car to somebody, you'd be talking about the fact that it was a vehicle that could be used to transport people or things, and it would have some mode of energy transmission, i.e. an engine. It would have some way of having wheels that would let it move forward, or some device that would let it move forward across the ground. Right? Could be wheels, could be tracks. There's lots of different things that are a vehicle. But what you're discussing is, as a concept, what's the concept of a car? Not, I have a car, it's a Corvette. No, you have, as a class, a thing called a car. It's a description of a potential that could be. Well, fine. When you make one, when you cause a car to come into existence, that's called an instance of a car. It is also called the object itself. You have a car object. Here, where it was a car class, it's just a description of the potential behavior. If you ever had a car, I'm not saying you do, but if you had a car, here's some of the things it would look like, and here's some of the things it could do. Well, now we actually have one. We have Eric's Corvette, because a guy can dream, right? This is an object. What object is it? It's an object that has a certain type. And it's a type car. It's a car object. You could have a user object, to use my example from over here. You could have an email sender object. But in every case, what this is you're saying, here's a description of potential behavior for a thing called a car, or a user, or an email sender. I want to actually have one. My program needs one right now. I'm going to make one. And that is the instance of that class. You can have multiple instances, and that's actually what you're planning on because of code reuse. If you're talking about users, you want to have thousands of users potentially on a website or a business application used in a company. You want every single one to have a description of its generic behavior and properties, but then when you make one, when you hire a new user or bring on a new person, you want to actually have them inside the program, inside your computer program, and you want to be able to say at the time you create them, well, here's the name of that person and the social security number and their date of birth and all that sort of thing, and here is how I can assign what job they have. All of those things are the actual instance of having a user. They're not the theoretical description of a user if you ever had one. That's the difference between a class and an object. An object is when you actually make an example one of the thing that the class describes. You actually ask for one to be created. Okay, good. So let's delve into this a little bit more. How does this work? You're going through your program. And you're going through it in order, boom, 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 there's all these steps, and you get to one where it says, I want a new user. And this user is going to have a name, Eric G, and it's going to have a social security number, 555, and some other numbers. And it's going to have a date of birth, 5/24, and the year that was a long time ago for most of you. This is when you create the object. These are the properties you'd like it to have. So how does this work? Your program has been executing and it gets to this point where it says, I want a new user. Well, over here in memory, it has a description of a generic class called a user. And it says, oh, you want a new user? Oh, here's what it has. It needs to have a name assigned. It needs to have a social security number assigned. It needs to have a date of birth. These are all properties. Oh, you're giving me those. Oh, good, okay. Now I'm going to make a new object. This object is user Eric G with the following properties. And now it gets the definition for what it's supposed to look like from the user class, which is stored in memory, and then it makes an actual user object, in this case, Eric G. So what does that in fact? Well, if you're going to look at this, actually, if you look at this class, one of the things in it, these are, by the way, properties. The property or characteristic of this user class would be things like name, social security number, date of birth. But then there's behavior, things it can do. Well, one of the behaviors is make a user. That's a very special thing it can do. It can make one of itself. Inside the definition of the class, you even describe when you make a new user, here's what to do. Here's how to assign the different points in memory and what the values are that you want them to be. That special behavior is called a constructor. A constructor. Literally, I want to construct one of these users now because my program told me I need one. What do? Well, I set certain properties like the name, the social security number, and the date of birth. And I do so with data that's been given to me by the program. That's a constructor. It's a specialized, defined behavior inside a class of what to do when you need to make an example of that class, an instance of that class, an object that is of type, that class. An object is just a thing. That's all it is, of a certain type. You could have a user type object. You could have a email sending type object. You could have a car type object. That's all it is. So that goes over we've just gone over constructors. Again, a defined behavior inside the definition of a class that tells what to do when you need to make one of these class types. Good. Now, why do you do this? What are the advantages? Well, there's a few different things about object-oriented programming that are, in fact, really strong advantages when you're making software. And you'll bump into these. And by the way, these are going to be relatively simplified descriptions of some of these concepts. You're going to go into these in great detail later on in your training. But let's look at a concept called encapsulation. To encapsulate means to put inside a little capsule, like everything's inside there. What does it mean in terms of code? Well, it means that if you have a block of code, software code, that's supposed to do something, like maybe do some sort of math operation or whatever, there are parts of a software program that will use that block of code, that pre-made bit of computer code. The users only know what this does. They don't get to see how. Right here on the outside, if you will, of this code is a box that these guys don't get to look through. It's a black box. Whoever's using that, whatever part of the program says, do the following. Let's use an example. Let's call it a multiply. You can give it numbers x and y, and we'll multiply them, and it'll give you whatever the product is. You don't get to know what's inside there as the user. Now, as a software developer, you do. You're going to write that. But the program that's using it only knows that if it gives two numbers, it'll get back the product of those two numbers. It doesn't know how. That, the how, is called implementation. Encapsulation is hiding away the implementation from the user. And you do it for a number of reasons. One of which is they don't need to know. The other one is that there are many, many different ways to do this. Some more efficient and some less efficient than others. You can use the one that you want to based on how quickly it performs without needing to know how it does what it does. And finally, one of the reasons for encapsulation is that inside this black box, it'll be working with data. Data that's only used internally. Not the data that's given to it or the data that comes out, but the data it uses while it's doing its job. You don't want any other part of the program to mess with that data and change it accidentally while it's doing its job that it was called upon to do. So encapsulation is a way of organizing your code so that nothing besides the code that's inside this block box, if you will, can actually manipulate the data inside it. It's all inside a capsule. That's encapsulation. And again, you go into much greater detail about this in the future. So one other concept related to object-oriented programming, and really it's related to anything involving the technology world, is the concept of state. You'll bump into this a lot. State means the condition of something. You could have a rock, and it's out in the sun, the sun's beating down on it, and at 9 in the morning, its state as regards temperature is that it's at 65 degrees Fahrenheit. And then at 3 in the afternoon, its state is that it's at 97 degrees Fahrenheit. State is only used for things that can actually change over time. Obviously. Well, where does this come in terms of programming? Well, here's a very simple one. In your first course, you covered hypertext markup language. The language is used to make web pages. Now, hypertext means taking text, some words, and giving them a way to connect to other linked documents, text documents. Here's the thing about these linked documents. They are static. That means they do not change state. They don't change condition. The way you write a page that's shown in 1997 If you don't change this code at all and you look at that page in 2015, that page is the same. Because all it describes is display the following text with the following modifications to appearance. Not display the following text with the following modification to appearance that are based on a changing time, but just, it's always this way. Always make it look this way. That is stateless. The basic challenge of the internet, by the way, of everything related to the World Wide Web, is that essentially it's stateless. When you call for a page on a website, that page was supposed to be just a simple text document with some changes to the appearance of the text or the images and not change over time. And yet, as needs of the public and of business have advanced, they want those web pages to have state, to display different information based on who the user is, and many, many other factors. So much of the technology you're going to be learning as a software developer is a way to make it so that these web pages have state characteristics, even though that essentially at the bottom, they don't. It's a lot of fun to make that work, by the way, and there's many different ways to do it. But that's state. Now, how does state relate to object-oriented programming? When you're looking at a class, again, we'll look at a class user. Remember, it's a definition of properties and behavior. If you were to have one, but when you actually make one, when you construct one, now the actual instance of a user, all the different properties inside it can change over time. The name could be edited, the date of birth, the social security number, the properties we made up in our example a minute ago. Now, this object of type user has state. And part of what you do as a software developer is actually throughout your program, make sure that you check or change the state of the different properties inside any specific object that you've made to parallel things that are happening in the real world. You have a user that needs their name edited. You're going to actually check to see that you have a name there and it's the one you want to change, and you're going to change the actual name for the new one, and then you're going to make sure that that got saved somewhere, it got stored, so that the next time someone checks on the properties of this user, it knows the new name rather than the old one. That's a very basic description. That's a basic covering of how state relates to classes in object-oriented programming. Okay, one more really awesome thing about object-oriented programming that you're going to get into is called inheritance. No, this doesn't mean that your grandfather left you a yacht. What it means is, if you're defining a class, in this case we're going to have a little fun and say our class is called car. Well, actually, let's go very, very high level and say we're defining a class called a vehicle. Remember that you're going to have properties and you're going to have behavior. Behavior is things it can do. Properties are its characteristics. What are the properties of any vehicle? Well, there would be body style. There would be color, if I can spell color. There would be year of manufacture, and more. There's lots, right? There could be manufacturer, who made it. These are all properties. That's what you want to know about a vehicle. What color is it? Who made it? When did they make it? What body style does it have? So you'd also want to know, like, what kind of engine does it have? Then there's behavior. A vehicle could accelerate. It could decelerate. It could steer. These are all things a vehicle can do. Good, fine. So now, you can easily make an instance of this, and you'd have vehicle number 1. And you'd have to set the manufacturer as Ford. And you'd have to set the body style as a coupe. And you could set the year as 1957. And then the color, fire engine red. And by the way, it's a complete coincidence that I just heard fire engine outside. And that's going down in posterity. And you could have an engine type, gas engine V8. That's a nice hot rod. Good. So, fine, it's a vehicle. But actually, that's pretty precise. There's lots of other things that can be a vehicle. Couldn't a tank be a vehicle? Couldn't a motorcycle be a vehicle? Absolutely. And couldn't you have a sports car, and you'd have a sedan, and you'd have a truck? These are all vehicles, aren't they? They all need to have these kind of properties: manufacturer, body style, color, year of manufacturing, engine. They all have these behaviors. So, but then they have things that could be different, that are specialized to that type of vehicle. Here's where inheritance comes in. Inheritance is making a new class. Let's make a class here called truck. And it inherits from this vehicle class. The vehicle class is the parent class. The truck is the child class. So what does that mean? Well, it means that it gets all of these properties and behaviors, but you can add in some. For example, one of the properties would be bed length. How long is the length of the bed on the truck? It would be towing capacity. You care about towing capacity on a truck, but you probably wouldn't on a coupe. And behavior, let's say that, behavior on a truck. I actually can't think of anything on that. Although let's say it's a dump truck. Then it would be dump the load. Good. The whole point is that you have these senior properties and behaviors that are part of the parent class. And a child class gets to use all of those properties and behaviors, but can add on more of its own. It has inherited those. And what that means is you don't have to rewrite this code. You just write the new ones, because these ones are already found somewhere. They're already defined. Again, code reuse is maximized. Good, so that's inheritance. Now, there's a thing called is-a and has-a. What this relates to is two other concepts in object-oriented programming you'll come up against. The inheritance one that we just talked about, and a thing called aggregation or composition. So, inheritance we saw before, which is taking a class and deriving another class from it that gets all that first parent class's behaviors and properties, and gets to add on behaviors and properties of its own. Aggregation or composition is making an object that comes from a class by using other objects from different classes. It's plus. It's has-a. Here's an example. You have a class called car. And then you have a class called engine. If you make a class, make an instance of a class, you could make a car, class car, you could have a Corvette. And you could have all of its properties, what color it is, all that sort of thing. Now you make a class of engine, which is a V8 gas engine. You could have another one that you made an instance of, which would be an electric engine. Those are both engines. your Corvette has a V8 gasoline engine. In other words, this instance of a car class has or is connected to this instance of an engine class. You have now aggregated or composed a very useful thing for your computer program to use, because your computer program may want to make changes to some of the characteristics or behavior of the engine, or make changes to some characteristic or behavior of the Corvette, the car itself, and yet these are all tied together. So if you change the engine significantly, it could affect something in the car. Again, the thing to know about all this in terms of object-oriented programming is that you are representing in code, in computer language, what happens in the real world. This is how objects in the real world behave. They are defined as your class, right? You have classes, you have descriptions of potential behavior, you have kinds of things. And certain kinds of things behave in certain ways and have certain characteristics. And certain kinds of things can be associated with, combined with others to form another thing entirely, i.e. a Corvette with a V8 gas engine. You can switch it out and have a V6 engine, but you'd be a wussy. You don't go fast enough. So that's is a and has a. This Corvette is a car. It's a member of the class called car. This Corvette has an engine. It has an instance of the engine class that is this exact set of behaviors and characteristics. That's is a and has a. That's inheritance and aggregation or composition. One more concept on object-oriented programming you're going to bump into is polymorphism. Sounds all fancy. Poly means many. Morphism means things related to change. Morph, change. Good. Watch a lot of comic book movies. That ought to be familiar. So what does this mean? If you have many related objects, object 1, 2, 3, and 4, and they're related because they come from different classes or child classes, they're related in some way. How do you treat that collection of related classes? And what polymorphism relates to is how behaviors that are defined in one class can be implemented and used in other inherited classes. And the rules for how all of that happens are actually relatively easy to understand, and you can get into them mainly in your C# classes, but they're a central part of object-oriented programming. Basically saying, how do you set up, in terms of writing a computer program, how parent and child classes that are all united by some commonality, how do you set up how to work with them and how the relationships between them work? That's the basics of polymorphism. One final note on that is that one of the main uses of polymorphism is taking a senior level class. Senior class has nothing to do with high school, thank goodness. A senior class, or the highest, it's also called the base class, which can then have child classes off of it because they're inherited. And defining behavior here in the base class that this child class can inherit, can do. And that other children, different child classes, can also use that same behavior. That's what polymorphism relates to as well. Good, let's cover these two things. A variable and a constant. You bumped into these a few times in your training so far. Just a further couple notes about them, because they relate to state. A constant gets set once. It's a value that you need. The value could be something like 2.14. It could be the value Steve. It could be the value red. The constant gets set. and it's never changed throughout the entire conduct of the program, the entire operation of the program. A variable, however, does get set, and therefore its state can change from one moment to the next. It could be things like, sales discount. So your program can change that based on the sales volume of the customer or what the day of the month is or such. Sales discount will change. It could be set as 5%, and then a few weeks later drops down to 0, and then a few weeks later goes up to 12.5. So that orders that get processed have a different sales discount applied against them. That's a variable. And again, you're going to learn all about these things. Make many variables. It's just a way to say, listen, I don't know what this is going to be yet, but it could change, and so I'm going to set it, and I'm going to give it a name, sales discount, age, color, name, and then I'm going to know, my program is going to know that it could change throughout time. And my program is going to be the one changing it a lot. There you go. Now, what's a function? This goes back to the most simple basics of a program. Now, remember at the beginning, programs were literally sets of instructions. And so on, times thousands. That at the very beginning were literally on big paper cards where there were holes in the cards relating to the instructions. And this card would get fed into the computer one instruction at a time. The computer would execute the instruction and do what it needed to do overall to have a program run. So that consecutive linear operation to a program is quite basic to a computer. Well, here's the challenge. What if there's some series of steps you need to do over and over and over and over and over again? You don't want to write out the same instructions over and over again. So what you can do is you can have them over here in a little self-contained box called a function. And here's your steps 1 through 8. And then over here where you have your main program, you're bopping along, you're doing all these instructions, and then here it says, do this function. So it goes and executes all those and then comes back and continues on, and then later on you do the same thing. You say, do this function. And it jumps over here, does a series of steps, and comes back. These ones can vary. The function is the exact same things every time. Prepackaged code modules, little bits of computer language that you're going to write, lots of them have been written for you, which is convenient, that you're going to write and you're going to call in your main program. That's what a function is. Now, basics of this is that very often the function needs some data to do its job. In that silly example I used a minute ago of a multiply behavior, by the way, that means functions. That means what are the things it can do. See, in this multiply behavior, it's going to need two different numbers. We're going to call them x and y because that's what every algebra teacher in the universe uses, right? You need to give them these two numbers and then multiply, and guess what? Your result, a, comes back. So the function needs to know, what are you going to give me? I'm going to give you x and y. And it also needs to know, what am I going to give back? That's called the return. So this function right here, you could give it 5 and 3. And it would give 5 and 3 to this multiply function. And it would give back 15. There you go. But the next time you want to call it, you might want to give it 2 and 7. And it'll give back 14. Either way, you don't have to write all these instructions out. You just write one instruction. Do this function with these parameters. These are called parameters. The parameter is what do you give the function? And then the return value is what you get back. So those are functions, and you're going to make a lot of them, and you're going to learn a lot more about how they work. Another question is, what's an index? An index is a pointer. It says, there is the thing. The index is not the thing. It's a pointer to where the thing is. Here's a very real example. It happens all the time. You're going to have a collection of data. Let's say it happens to be ages of students, because you have, we'll give it names so they have a little more fun. Names of students. You have a high school class, and you have Bob and Carol and Ted and Alice. And those of you over 40 know exactly why I use those names. So here's his set of data points. Now, you can put these into an array. Remember, an array is rows and columns. In here, we have rows 1, 2, 3, and 4, and column 1. That column is name. Thank you very much. The rows are, what's the value? So, in row 1, we have Bob. Row 2, Carol. Row 3, Ted. Row 4, Alice. The index is this. It says for this set of data that you have, this set of names of students, position 1 in the array that contains that data has a value of Bob. 1 is the index, Bob is the value. Index is not the actual thing. The index says where to find the thing. So, ready for a little weirdness? I mentioned this before in an earlier class. Most of the time, in almost every single computer language you're going to use, they don't start numbering these rows at 1. They start at 0. And if you don't know that, or you forget, you can run into a lot of heartache. Because you want the first element of the data. A set of data is composed of multiple elements. Element 1, element 2, so on and so forth. You want the first element. You're going to give it an index of 0 to find that. I'm sorry, you're going to give it an index of 1 because it's the first one. It's actually going to get you the second one, Carol. Be very careful with this. It will bite you in the behind, guaranteed over time. Not the least of the reasons why is that sometimes certain computer languages are odd and they actually do start numbering at 1. Just to be weird. But that's what an index is. It's a pointer to the actual data. All right, we're going to talk right now about how computers store data and how they use them when programs execute, how they use the data. And we're going to go down to the actual machine level for a moment and then step back to the bigger picture. In an earlier course, you learned about transistors. And remember, a transistor takes in electricity, 5 volts of it, and it decides whether or not to actually pass on that 5 volts. A 1 means yes, I passed on the 5 volts. A 0 means no, I passed on no voltage. So that's what a transistor does at its most fundamental basis. So how does that apply to memory, to storing things inside a computer? Let's say we arranged 4 transistors in a row. We're going to number them 0, 1, 2, and 3, because remember, you start at 0. It's just the way things work in the computer world. So here's a transistor. Literally, there's an actual little transistor inside there. It's a physical, actual device, arranged physically right next to other transistors. Now, I wrote what looks like zeros. What I'm saying is that each one of these boxes represents an actual physical transistor, physically located next to each other in your computer. And they're very, very, very small. So here's what happens is you need to store some data. And let's say the data you need to store is these 4 binary numbers, 1, 0, 0, 1. Okay. So what you're really going to want is to have a 1 here in this 0 or first element, a 0, and a 1. Okay. How do you do that? You get a transistor that once you set whether it does or doesn't pass electricity, then you can turn off the machine, unplug it from the wall, and it will retain its physical state, representing a 1 or a 0. So that next time when you plug it back into the wall and electricity comes through, this is still, in this case, allowing 5 volts to pass through, or in this case, not letting it pass through. You've taken this physical device, a transistor, and made it so it can remember whether there's a power there or not, whether there's electricity there or not. It literally physically changes state down inside this tiny, tiny little machine, this little tool, and next time you bring power to it, it'll do what it was doing before. That's a pretty cool trick, by the way. But that's how memory works. While the computer's operating, you set the value of these individual binary digits, bits. What you're really doing is you're setting the physical condition of a transistor. And the way it's constructed, it will remember that even after power goes away and then comes back. It doesn't remember, it's just physically changed inside so that when power comes back, it either does or doesn't pass on electricity. Good, so that's about as much of a look at this as you need, just to know that that's how it stores things inside the computer. And there are billions of these little sets of transistors next to each other. And most of the time, by the way, there's 8 of them next to each other. And sometimes there's 16. And in a lot of computers nowadays, there's 64 of them, all next to each other, and they're all representing one big coordinated piece of data. We're going way old school with 8. By the way, those of you who grew up playing video games may have heard of an 8-bit processor. Or when the Nintendo 64 came out, why that was such a big deal is because that central processing unit could handle, at first, when you had the first Nintendo that came out, it could handle instructions. It only had 1, 2, 3, 4, 5, 6, 7. It can only have 8 bits of data at a time. And it can only move so fast because the processor can only do one thing at a time. Now you build a processor that can handle 64 binary digit instructions that are that long all at once. And it can get that many more things done in a fraction of a second. And you all saw that when you were playing video games. They gave you much better image quality and response because that central processing unit could process more data more quickly. How do you measure that? In the bits. How big are the instructions? How many bits long are the instructions? So now let's step away from that tiny down into the transistor size look and a bigger picture. What we look at is how does your computer, central processing unit, in terms of input and output, make something appear on a screen. This is a really simplified description. This screen that you see actually is composed of tiny, thousands and thousands and thousands of tiny little physical dots. And what these are tiny points that can emit colors. Usually, that can emit a color of a red or a green or a blue. And when there's many of these all right next to each other, and you get different variations on red and green next to each other, or blue and red next to each other, or green and blue next to each other, you can start to actually see the full colors that you're used to seeing when you see a picture of the sun and a tree and all the colors and everything on it. But if you were to look really close, you'd actually start to see these individual dots of color. Those are called pixels. Many of you have heard that term before. So each individual picture is ultimately controllable all by itself. You can set what color it's going to be. And this is done thousands of times a second based on the instructions of your computer. So let's say we want to show this picture, and isn't that a nice picture of a sun and a tree and a little yard and dirt? I'm in the wrong business, that's all I'm saying. So here's this picture, and it's actually an electronic file. You took it with your awesome iPhone 6 Plus, and then you found a way to store it onto your hard disk drive on your computer. But now you want to see it on your screen. Your central processing unit will get an instruction to go down and get it from the hard disk drive and display it on the screen. But remember that this central processing unit only does one thing at a time. So it's literally going to go through this process I'll describe hundreds of thousands of times just to display that picture. It'll go down on the hard disk and it'll find the actual space on that disk where that information that represents the picture is stored. And remember, this information is just a series of ones and zeros, which, when the computer interprets them, can mean a red or a green or a blue, and exactly where in the picture that specific red or green or blue is meant to be represented. So very often, just think of it this way, it would start at the top left and get the very, very first value, is it a red or green or blue, and the next one, and the next one, and the next one, and so on. When we got to the end of this row, we'd go right down below and go through here, and in a split second, because these computers can operate so fast now, it would literally have read through all of this data. And it'll read one piece of data, and then it'll send it via wires to your actual monitor, to your screen, and it'll set the value, red, green, or blue, of that individual pixel. And then super fast, it goes out and gets the next set of data. And it says, oh, that one's meant to be a blue. And then so on and so forth. And it'll do this one tiny pixel at a time, this exact evolution. But it happens so fast that to you, you click on it and all of a sudden, boom, there's your picture. It appears on your monitor. So that's a bit more data about how the computer interacts with its storage, which is an input-output device, and a monitor, which is, especially because of touchscreens now, an input-output device, and how they all interact with each other. Now let's discuss a thing called data structures. You're going to hear all this stuff all the time. Data structures. Well, all this is how do you arrange data? And the thing is, there's so many billions of ways you can do it for every single instance that you kind of have to be able to learn the senior data of it, the senior principles behind it, right? But I'm going to give you an example to start. When I was going over on an earlier course, the concept of standard mail transmission protocol, what I was really defining is the word protocol. And this is basically saying what is the structure of the data. And if the source, the one that's sending the email message, and the destination, the receiver of the email message, both know the protocol to operate off of, i.e. they know the structure of the data that's going to arrive, then they can send it, they can receive it, and they can display it. So the data structure there, and again, this is probably not 100% close to what it is in the real world, but it's just an example, would be that when you receive this file, you'll receive an S, and then a colon, and then a space. And what follows after that, this text, this is the subject header, or the subject of the email. And then you'll get a B, and a colon, and a space. And then you get a bunch of text, and it might be quite a bit. And that text represents the body of the email. This is defined, you've just defined a data structure, and it could go on. What you're basically saying is, I want to arrange my data in a certain way. And the fact is, it doesn't really matter which way you do it, as long as you make it systematic and the same every time, duplicatable. You could have it backwards like that. Do your body and then your subject. At the end, they can arrange it however they want to on the screen, but they at least need to know what's the structure of the data that's coming. How is it arranged? That's what a data structure is. And there's as many of them as there are software developers and programs and opportunities to arrange data. Many of them have to be agreed upon, as in these protocols. Hypertext Transfer Protocol has to have the exact same format to the data, same structure to the data. But many of them you're going to define in your own programs. And I'll give you an example of how that'll go down with a really common data structure called a dictionary. You're going to make lots of dictionaries in your programming career. What it is a set of data, otherwise known as a collection of data. But specifically, it's arranged in pairs. That's a 1 and a 2. The first thing is what's called a key, The second thing is it's called a value. The key is, what's the name of the thing? The value is, what's it set to? What is its value? Here's an example. A key could be age. Another key could be weight. Another one could be height. Another one could be date of birth. But they're pairs. The value could be 45. The weight could be 195, but it's not. The height could be 5 foot 10 inches. The date of birth could be 5/24/69. These are key value pairs. That's a dictionary, right there. That dictionary could be called Eric Vidal. Vital statistics about Eric. So a dictionary is simply a collection of data organized in key value pairs. And you can think of hundreds of examples for how this might work. Like, you could literally have author, title, the ISBN, that's the number on the back of a book when it's published, key value pairs. And you can have thousands of these that a library would use. But that's a dictionary. And that is a data structure. This is how you've arranged the format of your data. Now let's make it a little more fun. Each of these key value pairs is itself a pretty important little thing. And each of these pairs could also be thought of as a single thing. And they're in a set, and they're arranged one after the other. And so they have an index. You can use indexes for a lot of things. The index is the pointer to the key value pair. You could actually say in pair 2, what is the value? 5 foot 10. In pair 3, what's the key? Date of birth. All right, let's get into decisions and looping and if, then, else and these sorts of things. This is the Robert Frost section of your curriculum. I took the road less traveled. I'm Poetry Geek, you're gonna have to live with it. Two paths diverged in a wood. He took the road less traveled. He had to decide. I'm not going to get all metaphysical on it and try to figure out why he decided that, but he decided. He may have had an if and then an else. He may have said, if the one on the right is less traveled, I'll take it. Else, I'll take the one on the left. What are you going to do? What you're dealing with here is decision making. You're dealing with branching. You're dealing with telling the computer what to decide in certain situations. And that is almost entirely your job as a programmer. Because if you go back to the example I had where you're executing consecutive instructions, instruction 1, 2, 3, 4, 5, but then right here, you want to call out a function. You want to go over here to use this function. What if you don't need it? What if this function, for example, is to multiply, except that one of these x and y happens to be equal to 0. But you don't want to multiply anything times 0. You're going to have to check if x or y is equal to 0, then skip the function. And it'll jump around it and go to 7. This is called, well, decision making or decision trees or if, then, else decisions. It's all the same concept. It's applying logic to whether or not you do or don't execute something. Now, you can make this a little more useful though, very, very often in computer programming, you have need of checking it through an entire collection of data and doing something to each element of the data. Let's go back to our list of students. Bob and Carol, Ted, and Alice. Now, what if we actually want to change these, because they're all in capital letters, and we want to make them all lowercase? You're going to need a program that can literally go through and it'll say, first go to item 0 in the index and set all but the first character to lowercase. And then go to item 1 and do the same thing. And then 2 and do the same thing. And 3 and do the same thing. You're looping through this instruction, the set all but the first character to lowercase. You're looping through a data set and executing that instruction each time. That's a loop.